Hello dear students, welcome to mathematics class. In this class, let us discuss the theorem. So here it is the statement of the theorem. If f comma g belongs to R of closed interval AB, means if f and g are Riemann integrable functions on the closed interval AB, then f into g. So this one is f into g belongs to R of closed interval AB. So therefore, if f and g are two Riemann integral functions, then product of them is also a Riemann integrable function. So let us prove this one. Since f comma g belongs to R of closed interval AB, since f and g are Riemann integrable functions, then it implies that f and g are bounded functions. F and g are bounded functions. So by the definition of bounded function, we can write that since f and g are bounded function, then there exists k greater than 0 such that mod f of x less than or equal to k and mod g of x less than or equal to k for all x belongs to the closed interval AB. So here this is nothing but it is the definition of bounded function. If a function is bounded, then its value is always less than or equal to some positive number k. And now mod f into g of x can be written as mod f of x into g of x, and this is equal to mod f of x into mod g of x. So now consider the product of the two functions f and g, then its modulus can be written as f of x into g of x, then again this is equal to mod f of x into mod g of x. Now here we know the value of f of x and g of x. F of x is less than k and g of x is also less than k. So therefore this is less than or equal to k into k, because f of x into g of x. So therefore this is less than k square for all x belongs to the closed interval AB. So again, by using the definition of bounded function, if the value of any function is less than or equal to some value k, then that function is called as bounded function. So therefore here mod f into g of x is less than or equal to k square. This can be considered, this k square is any real number. Let us name this as h. This k square equal to h, which is positive. Since k is positive, k square is positive, and that k square can be written as h. So therefore f into g of x is less than or equal to h. Then it implies that f into g is a bounded function by the definition of bounded function. And now f belongs to R of closed interval AB. So this is already given. Then it implies that for given epsilon greater than 0, there exists a partition. For given epsilon greater than 0, there exists a partition P1 of closed interval AB such that U P1F minus L P1F is less than epsilon divided by 2k. So here by using the necessary and sufficient condition for a function to be R integrable, here we can write that since f is Riemann integral function, then there exists, or for given epsilon greater than 0, there exists a partition P1 of closed interval AB satisfying the condition that U P1F minus L P1F is less than epsilon divided by 2k. And also G belongs to R of closed interval AB. So now again it implies that for given epsilon greater than 0, there exists partition P2 of closed interval AB such that UP2G minus LP2G less than epsilon divided by 2k. So here we know that the necessary and sufficient condition for a function to be Riemann integrable is UPF minus LPF is less than epsilon. So since epsilon is arbitrary value, here we have taken epsilon by 2k. Then now let P is equal to P1 union P2 be the common refinement of P1 and P2. So here P is the union of these two partitions, means that is the common refinement for both P1 and P2, because P will be greater than P1 and P will be greater than P2. Since P is the union of two partitions, that will be greater than P1 and P2, because P1 and P2 are the two sub partitions of P. So therefore now it is the common refinement for P1 and P2. Then we can write that UPF minus LPF, UPF minus LPF is less than or equal to UP1F minus LP1F less than epsilon by 2k, and UPG, it is the upper Riemann sum for the function G, and this is lower Riemann sum for the function G less than or equal to UP2G minus LP2G is less than epsilon divided by 2k. So now here, since P is the common refinement, then that will be greater. So then UPF minus LPF, the difference of upper Riemann sum minus lower Riemann sum of the function f in the partition P will be always less than or equal to upper Riemann sum of the function f and lower Riemann sum of the function f in the partition P1, since P is the refinement, and similarly for the function G also. And now we need to consider supremum and infimum for the functions f, g and f into g. So therefore let small mr, capital Mr, small mr dash, capital Mr dash, and small mr double dash, capital Mr double dash be the infimum and supremum of f, g and f into g. Now here small mr, capital Mr, Mr dash, capital Mr dash, and Mr double dash, capital Mr double dash be the infimum and supremum of the function f, means here Mr and Mr, these are the infimum and supremum for the function f, Mr dash, capital Mr dash, these are for g, and Mr double dash and Mr double dash, these are for the function f into g respectively on rth subinterval, which is equal to xr minus 1 to xr. Now for all x comma y belongs to IR, so let us consider the two values from the rth subinterval IR, they are called as x and y. We have mod of f into g of y minus f into g of x. So here let y will be greater than x. So now consider the greater value minus lower value, which can be written as f of y into g of y minus f of x into g of x. Now this is equal to f of y into g of y minus here add and subtract some quantity, so that is nothing but f of x into g of y plus f of x into g of y. So here we have added and subtracted the value f of x into g of x, then this remains as it is, that is f of x into g of x. So now here we have written this step, that is f of y into g of y minus f of x into g of x as it is, but we have added and subtracted some extra quantity, that is f of x into g of y is added and also subtracted from the same expression. Now let us separate the functions here. Now mod of, in the first two terms g of y is common, let us take it outside g of y, and remaining f of y minus f of x plus here f of x is common, so we have taken that f of x common, remaining g of y minus g of x. Now this one is less than or equal to, because here we know that mod f of x plus g of x is less than or equal to mod f of x plus mod g of x. If you separate the modulus of the sum of the two functions, then we get the inequality less than or equal to. So therefore here mod g of y into mod f of y minus f of x plus mod f of x into mod g of y minus g of x. Here just we have separated the modulus for each and every function. Now this is less than or equal to. Now we know that f of x and g of x are two bounded functions. So therefore their value is less than or equal to k, which is greater than 0. So therefore mod g of y is also less than or equal to k. Here mod g of y is less than or equal to k, since g of x is bounded and that is bounded for all the values of the interval a b. So therefore this y is also in the same interval a b, so therefore its value is less than or equal to k minus, and already we know that y is some greater than x. So therefore f of y is greater than f of x. So let us consider f of y as the supremum of the function and f of x as the infimum of the function. So therefore here we know that small m r, capital M r, these are the infimum and supremum of the function f. So therefore f of y can be replaced as capital M r and f of x is small m r plus, so here you can write in bracket, because mod f of y, that is the value of the function, then plus here this is k, since f is bounded function, and again mod g of y, they are the here m r dash, that is capital M r dash minus small m r dash. Since here f is already bounded function, then mod f of y must be less than capital M r and f of x less than small m r, because they are the supremum and infimum of that function. Now and on LHS, here this is f into g of y. Here we know that m r double dash and capital M r double dash, they are the infimum and supremum of the function f into g. So therefore f into g of y can be replaced by capital M r double dash minus small m r double dash. So it is the value of this f into g of x. Now applying summation to all this expression and also multiplying with delta r. Now let us see what happens. Summation over r is equal to 1 to n mr double dash minus mr double dash into delta r. We are applying the summation over r is equal to 1 to n and also multiplying with the delta r, which is less than or equal to k into summation over r is equal to 1 to n mr minus mr into delta r plus k into summation over r is equal to 1 to n mr dash minus mr dash into delta r. So therefore this one is less than or equal to, now k into, here we can take the summation for both the capital MR and also small mr. Then we can write this as summation over r is equal to 1 to n mr into delta r minus summation over r is equal to 1 to n small mr into delta r plus k into, here also the same thing, summation over r is equal to 1 to n capital mr dash into delta r minus summation over r is equal to 1 to n small mr dash into delta r. And on LHS part also we need to separate the summation for both the values. So therefore it is summation over r is equal to 1 to n capital mr double dash into delta r minus summation over r is equal to 1 to n small mr dash into delta r. So now here this capital MR double dash is the supremum for the function fg and small mr double dash is the infimum for the function fg. So now by using the upper and lower Riemann sums, we can write the summation of all these as, here whenever we are considering the supremum, that summation can be replaced as upper Riemann sum, and wherever we are considering the infimum of the function, then we can consider that as the lower sum for that respective function. So now here it is the supremum of f and g or f into g. So therefore it is upper Riemann sum of the function fg, upper Riemann sum of the function fg over the partition p minus, here small mr dash is the infimum. So therefore this is the lower Riemann sum of the function fg over the partition p. So therefore, and this one is less than or equal, here in both the terms that k is common, then we can take it that k common, remaining here summation over r is equal to 1 capital mr. This capital mr is the supremum for the function f. So therefore the first expression is the upper Riemann sum of the function f, that is upf minus lpf plus again here mr dash, that is a supremum for the function g, then it is upg minus lpg, that is upper Riemann sum of the function g, and this one is lower Riemann sum of the function g. Now this is less than or equal to, here it is k, then by using the result, so here it is the result, that is upf minus lpf is less than epsilon by 2k and upg minus lpg is also less than epsilon by 2k. So by using this condition we can put the values for lpf minus upf and lpg minus upg. So therefore here upf minus lpf is epsilon divided by 2k plus epsilon by 2k, then this one is less than or equal to k into 1 by k, you can take it common, remaining epsilon by 2 plus epsilon by 2. So therefore it implies that k and k get cancelled, then this quantity will be epsilon by 2 epsilon by 2. So therefore this is less than or equal to epsilon. Now here only this here upfg minus lpfg is less than or equal to epsilon. So therefore here it implies that upfg minus lpfg means the difference of upper Riemann sum and lower Riemann sum of the function fg is less than epsilon, So therefore it implies that f into g belongs to R of closed interval AB, because whenever UPF minus LPF is less than epsilon, then it implies that f is a Riemann integrable function, right. So this is the necessary and sufficient condition for the function f to be Riemann integrable. So therefore the same condition is true for the function f into g, because UPFG minus LPFG is less than epsilon, then it implies that f into g belongs to R of closed interval AB, means that is the Riemann integrable function. So therefore it implies that f into g is R integrable on the closed interval AB. So therefore here in this theorem we have proved that whenever f and g are Riemann integrable functions, then the product of those two functions is also Riemann integrable over the same interval. Whatever the intervals are given for the functions f and g, on the same interval f into g is also integrable.